Hi, and welcome back to Educator.com. Today we're going to talk about aromatic compounds. Benzene is an example of an aromatic compound. So if we take a look at benzene, some of the characteristics it has, we're going to have a better understanding of what all aromatic compounds have in common. So what makes benzene special? Benzene is a six-membered ring with alternating pi bonds. It has 3 pi bonds in there. And what makes benzene special is it has some resonance here where we can shift those pi bonds around, 2, 4, 6 electrons all moving around, delocalizing, and we can draw benzene with the double bonds as shown here where the vertical bond is on the left, or like we've done here where the vertical bond is on the right. So these 2 resonance forms for benzene, remember resonance means that neither of these structures really accurately represents what benzene looks like, and in fact the true structure is some kind of blend of those discrete Lewis structures. So sometimes we draw benzene like this. It's represented just with a circle inside of the hexagon. And anytime we see this, you might see this notation a lot when we're looking at other aromatic compounds as well. Anytime you see this circle, it means you have alternating pi bonds. So here we have a 6-membered ring. You're going to put as many alternating pi bonds, conjugated pi bonds as possible. So in this case, we could fit 1, 2, 3 pi bonds. If you look at a 3D sketch of benzene, you know that each pi bond comes from the overlap of p orbitals. So we can show one Lewis structure like this, where we have one pi bond here, and another pi bond here, and another pi bond here. But then if we take a look at the second Lewis structure, I've kind of tipped it over on its side so it's a little easier to see. We still have our p orbital on every carbon, but now the pi bonds have shifted to be between these 2 p orbitals and these 2 p orbitals and these 2 p orbitals. And again, thinking, recognizing that the actual structure is a blend of these, what that really means is we have these 6 pi electrons are actually completely delocalized throughout all of the p orbitals. So what you can draw, and that's what's nice about this structure that kind of looks like a hex nut, what's nice about that ring representation is it illustrates that in an aromatic compound like benzene, we have a cloud of electron density above and below the plane. This is a cloud of electron density above and below the plane. So benzene is a planar molecule, and we have a cloud of electrons above and below. So there's a few nice models that I'd like to share with you that illustrate this very nicely. This is a model that shows benzene, the 6 black atoms here, the carbon atoms, the sigma bonds are in gray, and so you can see that there's 1 hydrogen on every single benzene, and they're all 6 hydrogens and 6 carbons are all in one plane. And what this is showing is there's a p orbital on every single carbon. These are all sp2 hybridized. So there's a p orbital on every carbon. And what's nice about this model is it shows that those pi electrons are really delocalized above and below the plane. Rather than having discrete double bonds and single bonds and double bonds, really benzene has a cloud of electron density above and below like this. Okay, another model that's a lot of fun, but kind of huge, is this one. And this shows, again, same thing. This blue, each blue and green pair represents a p orbital. Remember, a lot of times we color them differently because they have different mathematical signs. And so on every single carbon, we have a p orbital. We also have a hydrogen pointing straight out. That's coming, that's in the plane of the molecule. And when we have this kind of space-filling model of what a p orbital looks like, you can really see how the p orbital on each adjacent carbon is touching and overlapping and interacting and sharing its electrons. So even though we can maybe think of this as 3 double bonds, really there is no distinction between a double bond and a single bond here because those electrons are equally distributed throughout the plane. So let's list some of the features that we've seen so far. It is a planar molecule. All of the carbons are sp2.